That's good. And have you completed the quiz or not all of you?
I have.
Yeah, I did it earlier today also.
Okay, no problem with the quiz questions. All good.
Some of them are a bit hard to follow. Like, I couldn't find like a lot of notes relating to it, going back and forth on notes. I hope I've done well.
Which one you faced the problem with?
Question one, it was like I couldn't find the notes relating to it, and when I did, I had to go back and forth a lot, and it wasn't like I couldn't relate a lot of the stuff.
I think it is only tension member, so it is similar to the one in the course material. But anyway, we'll have a look on it.
Do you know when the results will be out for the assessment and the test? Sorry.
Yeah, the assessment one will be released on Wednesday, and the quiz will be the Monday after.
Okay, that's great. Thank you very much.
No worries. And
I-
assessment 3 is now available on the course website if you want to work on it.
Great, thank you.
I just had an issue with the submission, Ahmed.
Yeah, no problem, Nick. Have you sent the submission via email?
Yes, I sent it to you well within the time limit. Just it just closed straight away for me, the submission box.
Okay, no problem. Like few of you has faced same problem, like the connection stale or it logged you out. So it's okay if you send it by email. It's okay as well. I will mark it.
Okay, thank you very much.
No worries. And for William, I just saw your post on the forum yesterday, so sorry if I was late to respond to you.
Oh yeah, no problem.
It's just
I
better
think
to,
most of
contact.
everything was provided on the exam anyway, so I
Okay.
think it was
Yeah,
yeah.
there's not much needed to go to the table on this one.
Yeah, I don't think it was too much of an issue. Thanks.
Okay, good. No worries. Just if you want like week one, just send email because sometimes I don't check regularly. So sorry for that.
Yeah, no, okay. I'll email in future. Too easy.
Okay,
Thanks.
thank you. Thank you. Okay, guys. So do you have any other issues, guys, with assessments or any other stuff before we start?
All good.
Okay, thank you.
Yeah, I have a question.
Okay, Bars, go ahead.
Uh, where we can see still for the assessment one is being graded or
Yeah, because the due date was Wednesday, so we will release it on next Wednesday. So maybe tomorrow or Wednesday it will be released.
okay, yeah.
So
Just
the
yeah,
assessment one grades will be released on Wednesday, and assessment two, the quiz will be released on next Monday.
next Monday. Okay. Yeah. And also about assignment 3 calculation, when will you upload the questions?
Yeah, it is already there. I can share it with you, but I just uploaded yesterday, so
Okay, yeah.
it is now
Yeah,
available online.
yesterday I checked and it was like no, I can see still the options, but there was no any file. Oh yeah, now I can see.
You can see it now. You find
Yeah,
it?
yeah.
Okay. So
Yeah.
that's
Thank
good.
you so much.
No worries. I just shared it with you as well here.
Yeah.
So if you don't have a look, can you see it now?
Yeah.
Okay. So this is the quiz. It is not very long one, but sorry, this is the assessment portfolio, the last one we have this course. So it's about also like calculating the load combinations and design members. So we have some members like T1 is a tensile like tensile force member,
Yeah.
and the column. So the column will be under normal and bending moment, similar to what we will do today. And also we have a rafter or beam,
Yeah.
and we have also connection. So this module 6 designs a connection connecting the column to the tie. Okay, so this is mainly the requirement of the quiz, sorry, of the assessment. And also
Yeah.
one thing here is we like using the loads, we need to draw the shear force diagram, bending moment diagram, and normal force diagram, and we need to check with Space Gas software. You mentioned before that you have used Space Gas before, right? Or
Yeah, I used a little bit, not too much. Little, yeah, only for the truss and yeah, joint.
yeah, it is simple one, so I can help you to draw the model, but just to link you to check our like your manual calculation with the software.
Okay, yeah.
Okay. And others, have you used the software? I mean, I think you have mentioned you have used it before, right? Or not all of you?
Not Space Gas, but I've used Strand.
Okay.
Yeah, same.
Okay, so I can edit it and add Space Gas or Strand 7.
I also have another question, if that's all right.
Yeah, sure.
So, at the top here, it says, please prepare a written report. So do you want it to be a written report or only calculations?
It just means like yeah, only the calculation, like do the calculation and so on. So
Yeah, so you're only interested in calculations. We don't need to write like an introduction and
no.
things like
I
that.
mean, yeah,
Okay, no worries, thank you.
just as a calculation and the requirements only here. So what
Yeah,
is the
explaining all
critical
the time,
combination?
the
Yep.
calculations, no need for an intro and all that stuff.
No.
Okay, great, thank you.
No, yes, thank you. So now let's start our topic for today. So today we will be looking at design of steel members subjected to combined action, similar to portal frames or frames in general. So combined action means that we have two string action at the same time. For example, we have axial force or normal, similar to column, and also bending moment or moment. So this will happen mainly in the frames, because the column and rafter in frames will have both of them. So this case is named combined action. Okay. There are several combined action, like for example, also rafters. In rafters, sometimes we need to check the moment and shear together. So this also a type of combined action. So this is mainly our topic today for week 5 module. So here start with designing of beams with full lateral restraint and design of beams without full lateral restraint, because last week we only talked about the beams or rafters subjected to moment, but only with full lateral restraint. So here we will talk about also if we don't have full lateral restraint to the beams. And the third part is design of structure members subjected to combined action. These members can be called beam column. And mainly we have in the combined action, again, axial and N and moment M. So these are the main string action we have. And again, the sources we have for this module is the standard and the two reference books if you want to have a look on them. Okay, so let's start with the design of beams with full lateral restraint. So here we have segments with full lateral restraint, typical to or according to clause 5.3.2 in the Australian standard. So if the segment with full lateral restraint, so a segment may be treated as full lateral restraint if it satisfies one of the following clauses, and the nominal member capacity, or if it is nominal member capacity calculated in accordance to clause 5 is not less than the following. So we have under this case two segments with continuous lateral strain and segments with intermediate lateral strain. For the segment with continuous lateral strain, segments with continuous lateral strain may be treated having full lateral strain, provided that both ends are fully or partially restrained, or the continuous strain acts as a critical flange. Okay, the other case is segments with intermediate lateral strain. Segment with intermediate lateral strain that divides the segments into series of subsegments may be treated as having full lateral strain, provided that, or if we have, both ends are fully or partially restrained, the length L of each subsegment satisfy this clause, or the lateral restraint acts as the critical flange. So the idea here in this one is about buckling, okay, or global buckling of the member. So as you know that here, so when we have the beam cross section, it may be subjected to like buckling. We have talked about this last week, so we might have something called, let's change the color here. So this one here. So the section might be subjected to lateral torsional buckling. Or LTB. So in some cases, we can consider it restraint against buckling if we satisfy these two cases. Okay, so this means that in this, in some cases, we can consider the beam full restraint against buckling. This means that no lateral torsional buckling will occur. Because from last week, we know that lateral torsional buckling reduces the capacity of the member. So in some cases, we can consider it full restraint or will reach the full capacity if we satisfy both this or one of these cases. So we will see later how to apply this in the problem or the design. But if the segments are fully or partially restrained to satisfy these three clauses, or the continuous restraint act as a critical flange. So for example, if we have this section here, let's explain this one here. So if we have this beam and we have the moment like that, this bending moment, so the critical flange in this case is the top flange because it is under compression. So if we have something to support the beam from both ends here, so this is what is meant by lateral restraint. So the beam is restrained, or the top flange is restrained from the displacement or rotation. Okay. So the next clause is segments with full or partial restraint at both ends. So a segment with full or partial restraint at both ends may be treated as having full lateral restraint if we have this condition: L over Ry less than or equal to 80 plus 50 beta m root 250 over a field if the segment is of equal flange I section. Okay, so again, if we have equal flange I section similar to this, so this condition or this formula apply, where Ry is the radius of gyration about the minor axis. So if we have two axes, so this is x-axis, y-axis, so y is the minor axis and x is the major axis. And the ratio beta m shall be taken as one of the followers, so can be taken as -1 or -0.8 for segment with transverse load. So if we have transverse load on this segment, so can be taken as -0.8, or the ratio of the smaller to the larger end moments in the length L. Positive when the segment is bent reverse curvature, or negative when it is bent in single curvature for segment without transverse load. So if we have a beam or a segment of beam with two moment, for example, this segment we have. So we have two moment, M1 and M2. So this ratio beta M will be taken as, for example, M1 over M2, where M1 is the smaller moment and M2 is the larger or the bigger moment. Okay, so this is the three cases we have. If we have full or continuous lateral strain, or intermediate or full or partial restraint at the ends. And here is some explanation of what we have. So restraint at ends and at intermediate points. So if this is our beam, so here we have supports at the ends. Here we have two supports at the ends and one intermediate here. And here we have two at the ends and two intermediate. So this is what is meant by full or partial lateral restraint. Okay, so restraint denotes an element or connection to prevent the beam cross-section from lateral displacement or lateral rotation about the minor axis or twist about the beam center line. So this to prevent or to reduce the lateral torsion buckling. Restraint at beam supports can also be supplemented by additional restraint along the span. So you might have restraint at the two ends, or you can replace them with some at the span. Okay, in the standard, we have some definition for the cross section. So we can have a section of full restraint or partial restraint, because this will affect the design. This will affect the design formulas in the standard. So we can have full restraint section, partial restraint, and we have also lateral restraint, and we have nil restraint or continuous lateral restraint and lateral torsion restraint. So 6 definitions we need to know. So for restraint, take the symbol F. It is a restraint that prevents the lateral displacement of the critical flange of the cross section and prevent twisting of the section. So if we have a restraint that prevent all the lateral displacement, so this is considered as full restraint section. Partial restraint, or B, this is a restraint that prevents the critical flange of the cross from displacing laterally, and partially it prevents the section from twisting. So partial restraint means we prevent displacement fully or completely and prevent twisting partially. For restraint, prevent displacement and twisting fully. Lateral restraint, or symbol L, is a restraint that prevents the lateral displacement of the critical flange without preventing the twisting of the section. So it's only preventing the displacement or lateral displacement, but allowing for twisting. Nil restraint, or U, So this is a cross section that doesn't comply with any type of the previous ones, fully or partially or lateral restraint. Or in other words, can be defined as restraint. So the displacement and twisting are not prevented or are allowed. So this can be considered as U or nil restraint. Continuous lateral restraint, C, is a critical flange or compression flange restraint provided continuously by concrete slab or checker plate or timber floor. Okay, with the requirement that the segment ends are fully or partially straight. So here in this one, no torsion buckling deformation occur even though lateral restraint are only applied. So if we look at this diagram, this figure here, so this is a steel beam or I-beam connected to a concrete or reinforced concrete slab. So in this case, this connection is considered as C or continuous lateral restraint. And similarly here, if this timber or checker plate, so same condition. Lateral rotation restraint, LR, a restraint that prevents the rotation of the critical flange about the section minor axis. So in this case, displacement is allowed and the restraint only preventing rotation or twisting. So these are few the definitions we will need in the design procedure of the beams. Some additional terms we need to have to know as well are critical flange. What is the critical flange means, or what is the critical flange indicates? The critical flange indicates the flange that would displace laterally and rotate further if the restraint were removed. This is the compression flange of simple beam or tension flange in the cantilever. So if we have like section, if this is a simple beam and the cross section here, so again this would be the moment. So the top flange is under compression, so the top flange is the critical flange. This is what is meant by critical flange. Critical section, the cross section that governs the beam design. Clause 5.3.3 of the standard note that the cross section in a beam segment or subsegment with the largest ratio of M star to MS. So the critical section is the section where the maximum moment apply, or the ratio M star is applied moment to the section moment MS, or section capacity. Segments mean portion of a beam between fully or partially restrained cross section. Restraint combination can be FF means fully restrained at both ends, BB partially restrained at both ends, FB means one segment, one end partially and one end is fully. Segment length L is the length of the beam between restraint type, fully or partially or lateral restraint. For a beam having FF or BB end restraints and no mid-span restraint, the segment length is equal to the beam span. So if we have a beam, this end is F, this end is F, and no other intermediate. So the segment length here is L, which is the beam length. So this is what is meant by this this statement here. An additional lateral restraint at mid-span would result in the subsegment length into one half span with end restraint FL or BL. So if we have same beam, fully here and fully here, but we add a lateral restraint here in the middle. So this is L by 2, or the segment span. and the connection now FF, and the middle is L. So this connection is FL. Sorry, this segment is segment 1, segment 2, segment 1 L FL, segment 2 also FL. Okay, so the segment length or the segment or the span is affected by if we have lateral support or not for the rafter. Subsegment means subsegment can be further subdivided into portion having at their ends at least lateral restraint L to the critical flange. Restraint combination can be again FL, BL, or LL. So if we have like two middle lateral restraint, so the segment can be subdivided to subsegment. Okay, so this can be subsegment 1, subsegment 2, and subsegment 3. Okay, so there's some definitions here we need to know to understand the formulas coming. And so there is a note here as well that the two symbols FLB and U are used to indicate the condition at two ends of the segment or subsegment. So these symbols are used to define the end conditions. F means full, L lateral, B partial, U nil. This indicates the types of lateral restraint at the both ends. And again, this some examples of restraining system that prevent the lateral or flexure torsion buckling of the beam. So this continuous, first one continuous because of the concrete slab. This one is lateral and torsional. So this prevent lateral torsional because of the connection here. Prevent both lateral movement and also the rotation. But here lateral only because the top flange is not connected, so it can rotate, but it cannot move because of the support here. Okay, so these are a few examples you can have a look on it. And also here some other example for the full restraint for beams. So here, one of the example, we have angle and welded to the top flange, so the top flange is fully prevented. Here as well, we have a fly brace that's connected to the top flange, so also preventing the lateral rotation and also the lateral displacement. Here as well, we have this connection here. So here we have fly bracing and we have purlin connected to the top flange. So the top flange is not allowed to move or displacement, horizontal displacement or rotation. And here this diagram for 5.4c is also another example for the partial restraint. Okay, so this some diagrams for the type of restraint. For 5.4d is example of lateral restraint. So this example here, the connection, the gusset is flexible gusset, so it can allow for rotation but preventing the lateral movement and so on. So here as well, rotational restraint. So all of these are types of restraint that can the beam segments have, and this will affect the design procedure for each of them. Okay, the division of a beam into segment and subsegment, similar to figure 5.5 here. doesn't affect the calculation of the design bending moment and shear in the span. It only affects the calculation of the reference buckling moment M naught. So this division or subdivision will not affect our calculation for moment, but it will affect the buckling capacity of the beam itself. Okay, which is M naught. We will have M naught in the formulas later. The formulas, the factor, sorry, alpha S and the breaking up of the bending moment distribution to respective beam segment and subsegment for reevaluation of delta or sorry alpha M. So the factor alpha S is just a breaking up of the bending moment distribution. So it reflects the redistribution or the distribution of the moment on the beam segment. Okay, similar to this example here. So if we have this type of beam, so we have this is the elevation, this is the plan view, and this is the elevation view. So in the elevation, we have a simple beam with cantilever. Okay, so if we have some loads like this, so the bending moment will be something. This is just an example. So this will be the bending moment. So we have negative moment here, positive moment here. So this is the bending moment, similar to this diagram here. But in the plan, if you look at the plan, this is the plan view. So in the plan view, we have fully or partially support here, no nil support here horizontally, and also we have fully or partially here, and we have lateral supports here, and fully or partially at the middle here. So the buckling of this one in horizontal direction will be something to this dotted line or this blue line. So this is what is meant by segment. The segment is only horizontally in the horizontal direction or affecting the horizontal direction or the lateral torsion buckling. But for the bending moment or vertical bending moment, there is no effect of the segments. Okay. So this is what is meant by this statement here. So if we look at the subdivision, we have this is a segment, this is a segment, this is a segment, this is another segment, this is another. So we have segment 1, segment 2, segment 3, segment 4, segment 5. Okay, so this is our segments. So this subdivision will only affect the horizontal direction. Do you have any question, guys, up to now?
Nope.
Okay, so thank you. So if we just to continue quickly in this one, in this section also give you the restraint definition in the Australian standard. So for example here, this given us figure 5.4 unrestrained cross section. So in this unrestrained cross section, there is no restraint, so the deflection is allowed and the twisting is allowed. Here another type is we have a pin connection between when we have the pin connection, this will prevent the lateral deformation, but the twisting will stay. So if we have a pin connection, so this can prevent lateral displacement, but allows for twisting. So this is the general case that we don't have any restraint. And the fully restrained, this standard give us some restraint of the fully restrained. So here the critical flange restraint effective twist restraint. So if we have a connection at top flange and bottom flange, so this will prevent no displacement and also no twisting. Okay, and here also there is a connection of the critical flange to the slab or so on, and also we have web stiffener. So this is another example of the fully restrained. On this one, we have critical flange restraint, but partial twist restraint. So at the top here, we have flexible. So the member is flexible. So this cannot be considered as fully restrained, but it can be considered as partial for twisting. And because the connection prevents the movement or horizontal movement of the beam, so it is not allowed for displacement. Okay, so this are just some few example or few the definition exactly in the standard. So you can have a look on this. It is just a repetition of what we have made earlier, partial restraint and rotational restraint and so on. So let's go to the calculation or the procedure of the bending moment capacity for the beam. So member capacity of segments with fully lateral strain. So this is our first step. If we have the beam with full lateral strain, so we have to follow this procedure. So the first thing is calculation of the nominal member capacity, MB, of a segment of with full lateral strain shall be taken as the nominal section capacity of the critical section. So just to simplify this, for rafter or beams, we have two capacities. We have section capacity of the beam and member capacity of the rafter of the beam. The section capacity MS and the member capacity MB. So if we have full lateral strain, this means that no lateral torsion buckling, and this will make that MB, the member capacity, will be equal to the section capacity. So the nominal member capacity is equal to the section moment capacity for full lateral strain. The nominal section moment capacity, MS, is calculating using this formula. MS equal to F yield times ZE, where the effective section modulus ZE is specified as these three clauses. Okay, and we have done this last week. So this is our section capacity. MS equal to F yield, the steel yield strength, depending on the steel type, times Z effective. Okay, which is the effective section modulus based on these three clauses. One of these three clauses, if the section is compact or non-compact, or cylinder. Okay, so we have these three types of sections: compact, non-compact, and cylinder. And the section cylinderness or lambda for a section with flat compression plate elements, the section cylinderness lambda s shall be taken as the value of the plate cylinderness lambda e for the element of the cross section which has the greatest value of lambda e over lambda ey. So we will have lambda e for flange or lambda effective for flange, lambda effective for web based on this one. So if it's flange, so B flange over T flange, F yield over 250. For web, B web over T web, F yield over 250. And we have the plate yielding limit cylinderness from table 5.2. Then we have lambda E over lambda E yield for flange and lambda E for web over lambda E Y for web. And the value of the plate is the greatest value of them. So we'll calculate both of them, and for the section, lambda E will be the greatest. Because the section is consisted of flanges and webs, so we'll calculate for flange and for webs, and the final or the whole section will be the greatest value of them. Where B is the clear width of the beam of the element outstand from the face of supporting plate, or the clear width of the element between the faces. So we have done this last week, but again, if we have like I section like this, so for flange, this is B flange, and this is T flange. For web, this is web height. So this is PW and this is TW. So this is the definition of the B and T for the slenderness limit. So for the first case, if we have full lateral capacity, so there is no new compared to last week. So we have MB equal to MS equal to F yield times Z effective, and Z effective is based on lambda E over lambda E yield. So we have three types: compact section, non-compact section, or cylinder section. So based on this, you can find ZE and then you can find MB. The new part this week or this module that we have design of beam without full lateral strain, which may be a common case if we don't have full lateral strain for the beam. So the value of MS doesn't equal to the value of MB. So what you expect, MS more or MB is more than MS? Do you have any idea? Nothing? Okay. So because MS is the section capacity, so this is the maximum that the section can achieve. So MS all the time will be more than MB in the case of no full lateral strain or beams without full lateral strain. So if we have this case here, So segment fully or partially strained at both ends. If we have both ends are full or partial restrained. So for open section with equal flange like I-beam, so MB or the nominal member capacity is equal to alpha M times alpha S times MS, alpha M alpha S, and should be less than or equal to MS. So the maximum again is MS, the section capacity, where alpha M is the moment modification factor, alpha S is the slenderness reduction factor, and MS is the nominal section moment capacity according to the previous clause for the cross section. So again, MS equal to F yield times Z effective. So now what we need to calculate here is the moment modification factor alpha M, which can be equal to 1 or a value from table 5.6.1 or from this formula here, and should be less than or equal to 2.5. Okay, so can be taken 1 or table 5.6.1. So let's have a look on this table. So this is the table 5.6.1, the moment modification factor alpha M for segment fully or lateral strained at both ends. So here is an example. If we have a beam with two moments, M and beta M times M, so this is the moment distribution. So this shall be the value of alpha M and not more than 2.5. So all these cases, so one of them shall be taken depending on what is the moment distribution on the beam segment here or here and so on. So take the value of the alpha M depending on your case. Okay, then the general formula is alpha M equal to 1.7 M star M over root M2 star square plus M3 star square plus M4 star square, all under the root, where M star M is the maximum design bending moment in the segment, M2, M4 design bending moment at the quarter point of the segment, M3 star is the design bending moment at the midpoint of the segment. So for example, if we have a beam with like moment like that, so we have the maximum moment in the middle here is M star, and M2 and M4 are if this L, so we have 4 quarters, L over 4, L over 4, L over 4, L over 4. So we have this is M2 and this one is M4 star, M4 star, and M3 in this case is the determining moment at the midpoint, so M3 star equal to M star. So this is just a simple example of the segment if we have bending moment similar to this. Okay, so these three cases are the values of alpha M. The next is the value of alpha S. The slenderness reduction factor alpha S shall be determined as alpha S equal to 0.6 times root MS over MOA squared plus 3 minus ms over MOA, where MOA is equal to M naught, where M naught is the reference buckling moment. So we have MOA and MO. MO is the reference buckling moment, or in other words, moment at which buckling occur. So at this moment, the buckling should initiate in the beam. So the reference buckling moment M naught will be given or determined using this formula. M naught equal to pi square E IY over LE squared times G J plus pi square EIW over LE or effective length squared, where E and G are elastic moduli. For steel, ES equal to 2 times 10 to the power 5 MPa, and G is called shear modulus. So E is the elastic modulus or Young's modulus, and G is the shear modulus, and this one is 80,000 MPa, and this one is 200,000 MPa, and IY, J, and IW are section constant, and we will find them in this can be taken from the design tables, design capacity table, given that IY is inertia about y-axis, J is the polar moment of inertia, and IW is the warping coefficient for the section. So this is the 3 parameters required to calculate the moment MO. LE is the effective length determined in accordance with the clause. So LE is the buckling length or effective length for the rafter. Okay, the value of E and G can be found in clause H and appendix in appendix H. So we have already given E and ES and G because they are constant for steel, but for J and IW and IY, this depending on the cross section, so it can be found from the tables. Okay, for segment with varying cross section, we can neglect this one. We don't need this one in now, so we can like skip this one. So this for section with like regular cross section, or the section of the whole beam is constant, no change in the section. So the formulas are applicable. So lambda S and lambda M and lambda and also MO are same. Okay, so this is the formulas for M naught or MO. So now for segments, other case we have a segment unrestrained at one end. For example, cantilever. So for cantilever, one end is restrained and other end is unrestrained. This may be like the case in your assessment C3. So for segment unrestrained at one end, the nominal member capacity MB is of a segment unrestrained at one end and at the other end both fully or partially restrained or laterally continuous or restrained against lateral rotation. So one end unrestrained, other end is restrained fully or partially. Okay, because one of them should be fixed. In cantilever, one of the ends should be fixed. So fixed means it is restrained fully or partially, or continuous restrained. So in this case, this equation with MO equal to the value of M naught obtained from formula equation 5.6.1 and the appropriate value of delta M given in table 5.6 or MB equal to alpha S times MS. So in this case, if we have one restrained and one unrestrained, so MO in this case will be equal to MOA, and you can use the previous case, or you can use this formula here. So we have MB, sorry, equal to alpha S MS. So this means that no lambda or alpha, sorry, M, no alpha M in this case. So where the slenderness reduction factor alpha S shall be determined as follows, and also the formula changed here. So alpha S equal to 0.6 times root MS over MOB all squared plus 3 under the root plus minus, sorry, MS over MOB, and this is alpha S, where MS again is the nominal section capacity, and MOB is determined by elastic buckling analysis and according with clause 5.6.4. Okay, so this is the case here. So we can take here MOB equal to MOA in this case for our calculation. So take MOB equal to MOA, and then we can find M alpha S. Then using alpha S, we can find MB. And if we use the first case, so sorry, this one here. So alpha M will be given using this formula. Sorry, this table 5.6.2. So if we have a cantilever with bending moment at the free end, so this will be the moment distribution. So alpha M equal to 0.25. If we have a concentrated load at the free edge, so this is the moment distribution. So alpha M is 1.25. And then if we have a uniform distributed load, so we have 2.25. Okay. And here in this end, the end is fully or partially restrained. So full or partial restraint, full or partial, full or partial restraint. So to summarize this one here, we have two options. Option one is use the previous equation, but just replace MOA with MO and use similar. The other option is using the formula MB equal to alpha S MS, and then find alpha S using this formula. So there's two options to calculate MB for one end restrained and one end unrestrained. Then in the formula, if you go back, we go back here. So in MO, there is a parameter which is L effective. So how to calculate L effective or the buckling length? So the buckling length or the effective length LE according to clause 5.3 LE shall be calculated using this formula. The effective length is equal to LE times equal to KT times KL times KR times L. KT is the twist restraint factor given in table 5.3.a, sorry, 5.36.3a, and KL load height factor, the next table, KR lateral rotation restraint factor. So if we look at the KT factor, it depends on the cases, the two ends restrained. So if F means fully lateral restrained, FL fully restrained and lateral restrained, LL lateral restrained, BB partial restrained. So KT can be equal to 1 or this formula or this formula. And also, if we look at cantilever, so we have U here, F here, so KT equal to 1. This is just an example. And for other simple beams, if it is fully, can take also as 1. If you have other conditions, so you can substitute in this formulas. And for the length L, the segment length for segment without intermediate restraint or for segment unrestrained at one end, with or without intermediate lateral restraint. Or L can be the subsegment length for subsegment formed by intermediate length. So again, as we discussed earlier, if we have this restraint, so this is L, this is L, or L over 2, if it is total L. So this is the length of the segment because we have a lateral or intermediate restraint. For the factor KL from this table, 5.3.6.3b, again, depend on the restraint arrangement within segment at segment end. So if we are calculating for the segment, so we have full, and full partial and so on. So load height position at the shear center or the top flange. What does this mean? This means that if we have a section, so the section can be loaded on the top flange. So this will be case 1 or this case, or other option is the section is loaded at the shear center here. So this is second case. So depending on the location of the load or the load height position, so can take the value of KL equal to 1 or 1.4. And as you can see, for the shear center, the factor is 1. But if the location changes, so it will be changed accordingly. Okay. And the third factor is the lateral torsion restraint, KR, table 5.6.3c. So again, the restraint arrangement and ends with lateral rotation restraint. So if you have a lateral rotation restraint, or not. So you have to come here depending on the restraint end. So again, if we have cantilever, so U and Foley at one end. So in this case, KR should be taken as 1. Okay, if you have a Foley, so if here, if you don't have any no rotational restraint, so this means that KR equal to 1 as well. So depend on the restraint ends and also the existence of lateral rotational restraint. Okay, so if we got the values of KT, KL, and KR, and we have L, so we will find the buckling length LE, or the effective length LE, and using LE, we can find the value of M naught. Using M naught or MO, we can find alpha S, and using alpha S, we will find the value of MB. So to calculate the the member capacity, it is a bit long procedure. We need to find the value of alpha M and alpha S, and the value of alpha S depending on, again, MO and MOA. MOA depending on LE. LE can be calculated as we just discussed, KT, KL, KR times L. So this how to find the value of MB. Do you have any question, guys, for the member moment capacity?
No.
Okay, thank you.
No.
Thank you. Okay, another method of design is design of using design by buckling analysis. You just can ignore this one here as well, just maybe for read, if you want to have a read. So this is another method to find MOA. We can skip this one. And here is the capacity table. We can use the capacity table for design as well, for universal beam. So if you have, for example, we will explain this later, but if you have a member like a beam, the tables give us directly it. So L effective, for example, here 8. Don't know if you can see see better now. So this table or this chart, how to use it? So for example, if we have a beam with 8 meters span, okay, if we have a beam with 8 meters span, okay, and the moment, for example, is given to us as well, like we know the moment. For example, it is like 310, or for example, 300 kilonewton meter. So here 8 meter LE, and the moment is 300, so it is somewhere here between 310 and 260. So what is the section we should use? So it's the closest to this one. So what is the section to use if we want to design this beam? We can use 610 UB 113, for example. So this is one option to use directly without calculating all the formulas and so on, but it's not the one we used in the course here. We need to follow the calculation. Another option, again, similar to here, if we have L effective same 8 meter, and we have the maximum moment as 300 kilonewton meter. So using this chart, actually the chart is drawn used the previous table. So for example, if we have 8 meter somewhere here, so 5, 6, 7, 8, we go up straight. Until we reach the 300 millimeter, sorry, 300 kilonewton meter, the moment, and we go horizontally. So the two lines intersect here. So it is between this section and this section. So which one to choose? The largest one. So this will be our selected section, which is 610 UB 113. Okay, and this for universal column section, if you want to use the universal column section. So same procedure. So this was for the beams with lateral and without lateral restraint. Do you have any question about this? Because next we will go to the next one, which is the combined action. So it
Seems
might
all
be-
right.
Yeah, it's just
Of
because
course, thank
just to
Yeah,
go to the
thank
details.
you.
No, thank you. Just to go to the details, so maybe a bit complicated, but when you solve an example, it will be straightforward. So now let's go to the next part, which is members subjected to combined action or beam column. So in this section, the beam column definition, according to or covered by section 8 in the standard. The definition of the beam column arises from the member subjected to combined action, axial force, and bending moment. So this section is subjected to axial or normal and bending moment M. So this is a combined action member. Compression members are almost always subject to combined compression and bending. So most of the time, or generally, the columns or the beam columns or compression member under normal and also under moment. So the section of the columns, especially in frames or portal frames, are subjected to axial and moment. The bending moment may arise from the eccentric application of the load, from the lateral loads applied to the column, and from the overall frame action. Another reason for combined action is even if the column is subjected to only compression, in some cases the load is not concentric. This means that the load is applied somewhere far from the centroid. If the load is far from the centroid, so this means that the column will be subjected to additional moment, which is if we have the eccentricity here E, so the moment or the applied moment will be the compression force times the eccentricity. So in some cases, if the applied load on the column is not eccentric or means, sorry, not concentric or eccentric, this means that we will have additional moment even it is small. So light trusses having only insignificant node eccentricity can be designed to neglect the induced secondary bending moment. So in trusses, you can neglect that, but in other structure, it should have taken into consideration. The interaction between the axial compression and bending moment produce three effects. So we have three effects due to this combination. Column buckling and bending interaction amplifies the bending moment. Axial compression forces reduce the bending moment capacity of the beam column. Bending moment about both the major and minor axes by axial bending reduce axial member and bending capacity. Okay, so we have three combination types. So the first one we have talked about this in the first two lectures, that we might have buckling to the compression member, so we can just amplify or increase the design moment due to the buckling. The second is we have N and M over the section, but about only one axis. So in some cases, we have this cross section. So we have normal force and one bending moment. The third is we have normal force, moment about X and moment about Y. So we have two types of moment. So we have normal force and M about Y, My, and M about X, Mx. So this case is called biaxial loading or biaxial bending. This case is called uniaxial bending. Uniaxial means one bending moment, biaxial means we have two bending moments. So this is the three interaction cases that we can have, normal and bending moment. And this diagram is the interaction diagrams between biaxial bending and axial loads. So in this case, this just tells the limits. So in any point in this diagrams, inside, this means that the column is safe. If the point outside, this means the column unsafe. And also another meaning of this is when you have zero moment X, zero moment Y, the value of the normal force is max. If you have a value of MB and a value of M here, somewhere on the curve, or somewhere here, so what happened to the normal force? Smaller N. So if you have when Mx or My exists, this will reduce the normal force capacity or the axial capacity, because this is like a limitation. So the high limit to reach in N is when the moments are zero, but when you apply moment, so the section will be weaker in normal, or the capacity will be reduced in normal. Okay. The design procedure, the design bending moment capacity of beam column is determined in the same way as for beams. The procedure adopted in this standard is to divide the verification combined action capacity into section capacity. We have section capacity is concerned with the checking that no section is loaded beyond its bending capacity. So we have MS. Member capacity, we have verification concerned with the interaction between buckling and bending, both in plane and out of plane. So we have MB and biaxial bending interaction. So we have MBX and MBY. Okay, so this is the three cases. And then let's go to the behavior of beam column members. There are three types of beam column member behavior: in plane behavior, and out of plane behavior, and biaxial bending. This is matching or coincide with these three cases. So for in plane behavior, where the member deformation from imposed loads and subsequent buckling deformation occurs in the same plane. This includes members bending about their minor principal axis, y-axis, that is, load and buckling deformation are only only in the xz plane, and the buckling is primarily due to column action, and in this instance, members bending about their minor axis cannot undergo flexural torsional buckling. Okay, so this is when the member in plane mode. So when we have a beam, so this is the plane of the beam. So there is no deformation out of this plane. Okay, so in plane means all the deformation of the beam will be in the same plane of the loads and the beam itself. So no deformation out of plane. Okay, so this means that no buckling will happen, or no lateral torsional buckling will occur in this case. Members bending about their major principal axis and only constrained to buckle about this axis, that is load and buckling deformation are only in the YZ plane. The buckling is due to column action as flexural torsional buckling, which can only occur about the minor principal axis is suppressed. So there is no option to buckle about its minor axis. So again, also for columns, if this is a column, we have, so this is the plane of the column. So the column will only buckle in the plane here, this direction or this direction, but it will not go outside of the plane. So this is called in plane behavior. So this is the transition or the interpretation of these two statements, that the members will buckle only about minor acts and nothing outside of the plane. The other mode of buckling is the buckling about or out of plane buckling, where the member deformation from imposed load don't occur in the same plane as the buckling deformation. Practically, this occurs from beam columns subjected to bending moments about their major axis, x-axis, with buckling deformation about the minor principal axis. The interaction between column buckling and flexure torsional buckling needs to be considered, as the later buckling mode is not suppressed. Okay, in this case, the buckling, the major, sorry, the dominant buckling will happen out of the plane. So if we have, again, this is the plane of the column. So the buckling will happen out of this plane. So it will buckle in this direction. Okay, just try to make it 3D. So the buckling will happen in this direction. Okay, so if this is the original axis, so this is the buckling out of plane. Okay, the third one is where the bending moment occurs about both principal axis and y-axis with or without axial load. The load or the buckling deformation present in this situation are combination of in-plane and out of plane with subsequent interaction effects. So the third case is we have buckling in both direction, x and y. Okay, this case show what we have discussed, combined axial compression and bending. Case A is the in plane about weak axis. Okay, so case A is in plane buckling about weak axis with column buckling. So in this case, this is the plane of the column, and the column is under load, so the buckling happen inside this plane, this way or this way. For B, case B, in plane bending about strong axis with column buckling. Okay, in this case, the plane, because of the moment in this direction, the moment here was in this direction about y, here the moment in this direction. So case B is still in plane, but the plane this time is this plane. So this is our column. So again, the buckling occur in the plane. So this is in plane, and this also is in plane. The third case, case C, is out of plane buckling. So this is case C. So here is the moment in this direction. So this is the column plane. So this is the column, but actually the buckling occurred out of the plane. Or maybe I can draw it like this. But as you can see here, if this is the plane, so the buckling occurred outside of the plane, like this. So this is the buckling out of the plane. So this is the modes of buckling in plane and out of plane for uniaxial column. For biaxial, the buckling will occur in both directions. The design action for beam column elements to check the section capacity at the section, the design axial force. So we have N star is the axial force, which may be tension or compression, can be tension or compression. This is the first one. And the design bending moments, we have bending moments mx star and my star, where mx moment about x-axis, my is moment about y-axis, shall be the bending moment about major axis and minor axis. To check the member capacity, the axial force shall be the maximum axial force in the member, and the design moment are the maximum bending moment. So we have three straining action in this case. One is normal force, 2 and 3 are the bending moment. Mx and My stars are the design bending moment resulting from framing action and transverse loading and include the second order effects. So from the bending moment diagram and so on, you can find Mx and My. The design bending moment shall be determined one of the following method. First order analysis. So we are only using this one here. First order analysis by modifying the first order design bending moment using the appropriate moment amplification factor determined accordance with this clause. So this case can be used manual calculation or software, the option of linear elastic analysis. Okay, we don't have to use this in this course, but for your information that we have other like advanced types of analysis like second order analysis, which take more effects like the buckling or the member buckling effects. So these are other options of analysis. We don't need to use them in this course. But the next is how to design or how to find the section capacity and member capacity for members subjected to combined action. So this is the design procedure of this type of member. So the first case, if we have uniaxial bending moment about the major axis, so we have N and Mx. So this is the first case. If this our section, so what we have is this is X axis and this is Y axis. So we have applied normal and applied Mx this way or this way. So we have moment and M about major X. So the maximum moment Mx star should be less than phi Mrx. So this is the applied moment. And this is the section capacity. Where phi is the capacity factor, it will be 0.9 or in table 3.4. Mrx is the nominal section moment capacity reduced by the axial force, tension or compression. So Mrx is a section capacity but reduced due to existence of N. So Mrx equal to Msx, which is the section capacity, times 1 minus N star over phi Ns. Okay, so this is the general rule. For doubly symmetric I section, for special cases like symmetric section, for compression members, Kf equal to 1, the shape factor, if you remember. If the shape factor is 1, and for tension member, you can take the formula as Mrx equal to 1.18 Msx times 1 minus N star over phi Nx. For compression member, where Kf is less than 1, so if Kf is less than 1, the shape factor less than 1, so this is the formula. Where Mrx equal to Msx times 1 minus same formula but multiplied by this factor, where lambda w and lambda wy is the values of lambda e and lambda ey for the web. So lambda w is lambda e web, lambda wy is lambda e web yield. Okay, where Msx or Msy nominal section capacity for about x and y determined in accordance with clause 5.2. So Msx or Msxy is the normal Ms calculated earlier in week 4 and week 5. Ns also is the section capacity calculated earlier in the compression member design. Okay, So nominal section capacity accordance with 6.2 for axial compression or axial tension. So this is the first case if we have uniaxial bending moment about major x or x-axis. If we have second case is if we have uniaxial bending about minor axis y-axis. So if we have a section and we have this is x-axis, y-axis, and we have normal force at the middle, and we have my or minor x. In this case, my star equal to phi, sorry, less than or equal to phi mry, where my is again section capacity. Sorry, what is m star? M star is the applied moment. Phi mry is the section capacity, and it is reduced due to existence of n. So similar to the first case, but my. So phi capacity factor equal to 0.9. MRY nominal section capacity equal to MSY times 1 minus n star over phi ns. And another way to calculate MRY directly can be calculated as one of the following: doubly symmetric section, compact section. So 1.19 times 1 minus n star squared, n star over phi ns squared should be less than MSY. For rectangular or square hollow section, compact section, so we have similar equation but 1.18 MSY and 1 minus n star over phi ns less than MSY. So this is the second case, similar to case 1. The third case is the biaxial moment. In the biaxial moment, we have 3 applied string action, n star, mx star, and my star, all applied. So the formula becomes this one here. So we have n star over phi ns plus mx star over phi msx plus my star over phi msy should all be less than 1. Okay, so this is the case, and this is axial. This is bending moment about x, and this one is bending moment about y. For double symmetric section, I section, and rectangular section, hollow section, any symmetric section, compact. So the formula can be mx star over phi mrx or to the power gamma plus my star divided by phi mry to the power gamma, and should be less than 1. Where mrx and mry calculated as we calculated earlier in the previous procedure steps, and gamma 1.4 plus n star over phi ns, and should be less than 2. So all of this procedure, three types of cases or 3 types of loading cases for section capacity. We should have also member capacity. So we have member capacity for combined action. So the first three or the first part was section capacity and second part is member capacity. And here again we have three cases. We have in plane capacity. So for in plane capacity for compression member, a member bent about principal axis shall have sufficient in plane capacity to satisfy the following. So we have M star should be less than phi mi, where M star is the applied moment. So this is the first case or A in plane behavior. So the applied moment should be less than phi mi. So M star the design bending moment, phi the capacity factor, so phi equal to 0.9. And mi is the nominal in plane member moment capacity. So mi is member or in plane member moment capacity. And mi equal to ms times 1 minus n star over phi nc, where ms nominal section capacity, n star design axial compressive force, nc nominal member capacity. So all of this have been calculated earlier, or we have spoken about them earlier. And another option for doubly symmetric section, you can use this long formula here, where mi equal to ms times 1 minus 1 plus beta m over 2 to the power 3, all multiplied by 1 minus n star phi in over phi n c plus 1.18 times 1 plus beta m over 2 to the power 3 times root 1 minus n star over phi n c, and should be less than mrx or miry depending on the moment star is mx or my, where beta m is the ratio of the smaller to larger bending moment. mrx or mry is a nominal axial section capacity about the principal axis, if my or mx. If the member is subject to tension, n star, the design bending moment shall be satisfied clause 8.3, or in other words, member capacity is not applicable, so the section capacity equal to the member capacity. So if we have tension member, so actually there is no buckling in plane will happen. So there is no meaning for mi, and then mb in this case will be equal to ms. Okay, so because the tension doesn't cause buckling, so that's why the capacity of the section will be equal to the capacity of the member. The second behavior, the second type of behavior is out of plane. Again, we have compression member. For compression member subject to axial n star and bending moment mx about their major axis. So here for out of plane, we have mx star as one case, my star as a different case, which may buckle laterally. We should satisfy the following: mx star applied moment about x should be less than or equal to the capacity phi mox, phi equal to 0.9, and mox will be the nominal out of plane buckling equal to mbx times 1 minus n star over phi ncy, where mbx is the nominal member capacity of the member without full lateral strain and bent about their major x-axis. So MBX is a member moment capacity of unrestrained member. NCY is the nominal member capacity in axial compression. So these two have been calculated earlier in other types of member. Or for member without transverse load and compact and doubly symmetric. So you can use, so for all formulas, if we have compact and symmetric section, there is another or a simple calculation given directly. So MOX equal to alpha BC times MBXO and times this root, where 1 over alpha BC equal to this formula to find alpha BC. MBXO is the nominal member capacity without full lateral strain. NCY nominal member capacity. Beta M ratio of smaller to larger. So all of this has been calculated earlier. And the new parameter here is NOZ, is the nominal elastic torsional buckling capacity of the member and can be calculated using this formula. NOZ equal to GJ plus pi squared EIW over LZ squared divided by IX plus IY over A, where E and G elastic moduli, AW, IX, IY, and J are section probabilities. LZ is the distance between partial and full restraint. So if we have a column and we have like full restraint, full restraint, so this should be LZ. So this was for compression member here. If it is a tension member, a member is subject to design axial tension and design bending moment mx star. So we have still measure moment, which may buckle laterally. So we have mx star or mx star, the applied moment. Should be less than or equal to phi MOX, which is the member capacity. Where phi is the capacity factor 0.9. MOX is the nominal out of plane buckling capacity. So MOX equal to MBX 1 plus. So here, because it's tension, so it is plus because it is a tension. In the compression member, it was negative. So this is the difference. MBX is the nominal member capacity done before. NT is the nominal section capacity in axial tension. MRX is the nominal section moment capacity reduced by axial force. So this is if it is tension, so the difference would be the positive sign instead of the negative sign in compression.
Sorry, Ahmed, I just need your help. Are you able just to check your email? I just have some issue with my quiz.
Okay, no worries. I will check the email after the lecture. So have you sent the calculation by email?
No, I haven't, but it's just I'm still doing the quiz now, and it's just I don't know, I couldn't open it. It says it's open in another window, but I didn't open it in another window. So I'm not sure why it's saying that.
Okay, can you send email to Goyang?
As to who, sorry?
Guyang, he is a unit assessor and he can help you to solve this issue. Do you have the questions or you don't have the quiz question?
I have the question, but can you send where can I find his email?
He's on the course information. His name is Guoyang.
Hmm,
Okay.
I'll check now. Hmm, and in the contacts. Oh, okay. Okay. What if he didn't answer? Do I just submit it and send it to you by
Yes,
email?
by email. Yes.
Okay, thank you.
No worries. Okay, so again, just to go back to the formulas we have. Just minimize this. Okay, so this is again the table for phi. So we have already discussed this before. So most of the calculation or most of our calculation, phi is equal to 0.9. Only few of them is in the connection, for example, it become 0.75. Also on the connection here become 0.8 in some of them. So most of our calculations, like member subjected to bending, axial compression, axial tension, combined action. So phi is generally equal to 0.9. So this is phi, and so we have up to now two of the behavior, in plane and out of plane. So the third one is biaxial bending capacity. So if we have biaxial bending capacity, so we have mx star and my star plus n star. So the first case, if we have a compression member, so member subject to design compression and design bending moment mx star and my star. So the design moment shall be satisfying this formula. So we have mx star over phi mcx to the power 1.4, my star over phi miy to the power 1.4 should be less than 1, where phi is 0.9, mcx the lesser of the nominal in plane and the nominal out of plane bucket. So mcx is the smallest or the lesser of mix and mox in plane and out of plane about x. MIY is the nominal in plane member capacity of IY of y axis. So MIY is the nominal member capacity about y. So if it is tension member, so similar equation, but the difference is instead of member capacity, it becomes section capacity. So for tension, because tension doesn't cause buckling, so we have MTX, the lesser of nominal section capacity, MRX, and the nominal out of plane member capacity. So here we have the lesser of MRX or MOX. MRX for in plane, MOX for out of plane. MRY is section capacity in Y. Okay. So these are the three cases. So if we summarize this, we have three checks or three behaviors of the combined action. But we will have only the three if we have biaxial, but in some cases, if we have only one moment, so we have two behavior. The first one is in plane behavior. The second one is out of plane behavior. So this should be there if we have M and M. And if we have, just to add, we have Mx and My and N. We have N and Mx and My. So we might have the third one, which is the biaxial behavior. Okay, so this is what we have about the combined action, and any member of the frame shall be subjected to this combined action. So you have to consider the combination. And some notes about the beam column members. The beam column design process is very complicated and it involves trial and error. Designer can modify the outcome of the design by exercising control over the position, type, and lateral strains. So you can add lateral or remove lateral strains to make the design more economic. Shelf weight of members made of rolled or tube section can reduce compression capacity significantly. Self weight should be included in design action. So the self weight, because you add lot more uh, lot like gravitational weight, so it can reduce buckling. So the self weight should be taken into consideration because it is reduced buckling. Adequacy and efficiency and economy of the solution should be subjected to row appraisal, and what if analysis should be taken. So just general notes here. And this is a summary of the design procedure. So the following procedures begin with lower tier approach, which may be suitable for ordinary building structure, but tends to be conservative. So this procedure are conservative design. Thereafter, more economical high tier design are highlighted. So the first step of our design for a frame is the frame analysis. Analyze the frame for design action and their combination given the most adverse action effect. So I need to, like, for example, calculate the loads, then load combination, and then analysis. So drawing bending moment diagram, shear force diagram, and normal force diagram to design the members. Carry out a second order analysis or moment amplification producer to determine and then determine the effect length of the column. Then determine the nominal buckling loads and moment amplification factor. So all of this comes under the analysis to draw the normal and bending moment and shear force diagram. Then data assembly, to the complete set of data required for manual or computer calculation. So you need to extract or calculate the design effect. So you need to find the maximum design axial load. So if you have a frame, for example, and this is a bending moment diagram. Sorry, this is our bending moment diagram. So you need to, and this also our normal force diagram, for example. So for example, if we are designing column C1, so we need to calculate the maximum moment, Mmax here. This is Mmax for the column. And somewhere here is Nmax. So you have to find M star, M star. So we have this here is N star, this one here. And here is M star, and this is Mx, so this is Mmax. So using the analysis, design axial load and design bending moment about x at end A and B. For example, here, if we have two ends, so the moment here M equal to 0, M equal to Mmax. And if we have another moment about My, so the design actions will come from the analysis of the frame. Then design bending moments are bending moments obtained from second order analysis or first order analysis with the amplification factor. So if you have second order effects, so you need to consider using the amplification factor. Member and section data required. So we have the length, actual length, Lx actual length between restrained about X, Ly actual length about Y. If yield, the design yield strength of steel, depending on steel grade. A net, Kf, shape factor, Zex, all these are probabilities of the section, can be found in the capacity tables. Then the third step is the effective length probabilities or effective section probabilities. So we need to find lambda effective or lambda E and lambda EY and check if the section compact or non-compact and so on. Then effective lenses, column action. So for simple method calculating the column effect length, we have this type of calculation like Lex equal to Ke times Lx, Ley equal to Ke times Ly. If you remember from last week, the simple formulas from the table, if it is bin, so K equal to 1. If it is fixed, so equal to K equal to 0.7. And if it is fixed bin, so we have K equal to 0.85. So this is the effective length if needed or if we are designing a column. Then step 5, we have column cylinderness. So cylinderness reduction factor refers to the reduction of the section capacity to account for the column cylinderness. So we have alpha Cx and alpha Cy for the member capacity of axial compression member. Then step 6, axial compression capacity, NS member, section capacity, and NC member capacity. Using these two formulas, depend on the parameters given. Then we have to N star should be less than the minimum of, or should be less than NS and should be less than NM, or sorry, NC. Phi NS and phi NC. This is the section capacity, this is the member capacity. Then the moment capacity, because this member has axial and moment, so we have both of them. So then second step is the moment capacity. So we need to calculate the cylinderness of the section, alpha S, and the reference buckling moment, MO. Then alpha S, or the reduction factor, equal to this formula, where section capacity MS is obtained from MS equal to phi yield times ZY, Z effective, And the reference buckling moment MO is using this formula, where the effective length LE is using this formula, KR times KT times KL times L. The nominal member capacity is MBX equal to alpha M alpha S times MSX, where alpha M is the moment modification factor and MS is this one here, Z effective times F field. Okay, the design moment capacity check with phi equal to 0.9 is one of these two, depending on the type of moment. If we have MX, so check with phi MSX, sorry, MBX because it is member capacity, and MY star less than or equal to phi MBY because it is member capacity. The beam column design process is slightly complex and may involve trial and error, so the designer can modify the outcome by expressing the control. Okay, the second step is step 8. So reduce section capacity due to combined action. So step number 8 is section capacity due to combined action. So this is basically reduction in the bending capacity subject to combined action, compression and uniaxial bending. So this case we have M and N, and M can be MX or MY. So using the lower tier for any section bent about major axis, MRX is equal to the nominal section capacity bending about the x-axis used by axial force, tension, or compression. So this is the value of MRX. So MRX is actually the section capacity but reduced with this factor 1 minus N star over phi NS. So this is the MRX. And for compact doubly symmetric section, square hollow section for tension member and compression member with Kf equal to 1, we can use this formula. And if less than 1, we can use this formula. And for any section bent about the minor principal axis, MRY is the nominal section capacity bended about y-axis reduced by axial force. So this is if it My. So if it is My, so MRY equal to MSY times 1 minus N star over phi NS. And for symmetric section, compact, we have this formula. And the checks are again MX star compared to the section capacity, phi MRX and MY star less than or equal to phi MRY. Yes, step number 9 is if we have biaxial moment, so we have to use this interaction formula, where is N star over phi NS plus MX star over phi MSX plus MY star over phi MSY should be less than or equal to 1. Or for compact and symmetric section, this formula can be used where gamma is 1.4 plus N star over phi NS and less than 2, and MRX and MRY are the section capacity for the section calculated as before. Step number 10, if you have in-plane member moment capacity behavior, so we have MIX and MIY. So one of these cases. So MIX, if we have MX equal to MSX times 1 minus N star over phi NCX, where NCX is the member capacity of the member under compression. And then step 11, the out of plane member moment capacity. So we have MOX equal to MBX times 1 minus N star over phi NCY. And step 12, if we have biaxial moment, so we have this formula where MCX is the lesser of MIX or MRX, and MIY is the member capacity of the member about y-axis. Okay, again, also the self weight of the member reduce the buckling, so should be taken into consideration. And then final step is design overview to satisfy the economy of the solution. Okay, so this is just a summary for what we have done for the beam column members, and that's the end of this module. Do you have any question, guys, for the design of beam column members?
Not at this moment.
Thanks, Nick. Do you have any comments, guys, or any other question?
All good to me, thank you.
No, as you know, all cases will not happen at once, so we just take all the cases just for explanation. But when you are designing a member, not all of that will be included in one case. Okay, are you aware of that?
Yep.
Okay, that's good. Okay, so can have, do you have the tutorial example? We can have some example. Just give you time to define this one. Okay, can you please try this example number 2, please? You guys, do you have the questions? And I think the answer as well is provided. So can you have a trial with this one, please? And let me know if you have any question.
Yep.
Yeah, good, thanks.
No worries, thank you.